Okay, in this video I'm going to continue with the discussion of integrated optic devices and tell you about directional couplers. But this topic also goes beyond integrated optics because there are such things as fiber directional couplers, and I'll explain those at the end of the video. But the basic idea is that instead of just having splitters where we have 1x2 Y branches, we can make a much more flexible device called a coupler, and I've shown it schematically here where we have two inputs and two outputs, but basically what we're doing is we're bringing two waveguides very close to one another here over some distance, okay? And that has the effect of causing light to be transferred from one waveguide to the other. And I'll show you schematically how that works here. I'm going to draw the two waveguides here next to each other. So these are the two cores, and this is a cladding region between those two cores. But what happens is that light, if it's brought in on one of the waveguides, let's say that we've got a symmetric waveguide and we have this mode of light coming in on that waveguide, no light in waveguide number 2. What happens is that the light is inevitably, some of the mode is inevitably out in the cladding, and this is called the evanescent field. Well, what happens is if the waveguides are close enough to one another, light starts leaking from one waveguide into the other. And what I'll do is I'll go ahead and draw a sequence of diagrams where at the end of this sequence the light is completely over in waveguide number 2, whereas it started off completely in waveguide number 1. So what happens here is that we have waveguide number 1 losing light and waveguide number 2 gaining a little bit of light, and then waveguide number 1 has lost most of its light, waveguide 2 has gained a little bit of light. But basically what happens is we have the optical power is essentially being transferred from one waveguide to the other in this device. Okay? And again, that occurs because of the evanescent field. And when you have two waveguides, now let me draw two waveguides sort of like this in a horizontal configuration. What's going to happen is that the optical power will go back and forth between those two in a sinusoidal way. Okay, and the coupling length is the distance over which the power completely transfers from one waveguide to the other. Okay, so this pair of waveguides is, let's say, exactly 1, 2, 3, 4, 5 coupling lengths. And you can see now where the flexibility of this type of device comes in. Depending upon the length of the coupling region, we can get the light to exit one waveguide or the other, or we can vary the length of the coupling region to allow for any fraction of light to be coming out the two outputs. And so let me draw my coupler again in schematic and label it a little bit. Here's my waveguides. Here's the top waveguide. Here's the bottom waveguide. And I'm going to call this input power P1. I'm going to call this output power P2. And I'm going to call this output power P3. Normally we don't use all four of the possible inputs and outputs, but sometimes we do. This distance here is going to be labeled the distance L, and this is the coupling region. So this is called the coupling region. Okay. And so for a 3 dB coupler, what we're going to do is we're going to ask that P2 is equal to P3 is equal to P1 minus 3 dB minus excess loss. Okay. In other words, half the light is at each of them. In other words, what we're going to have to do is we're going to have to set L equal to half of the coupling length. Okay? And that will give us the situation where the optical power is then halfway between waveguide 1 and waveguide 2, and this will work. And so I guess I could add an intermediate situation here where the light really is 50, 50. Okay. At half the coupling length. Okay, so this is what we're going to do to make a 3 dB coupler. And it turns out the mathematics of this is all fairly straightforward. The equations for the powers at the outputs are as follows. P2 over P1 is the cosine squared of pi L over 2LC, and P3 over P1 is sine squared pi L over 2LC. Remember, L is the length of the coupling region, and it is usually measured in units of the coupling length. And so here we can see that L over LC, well, when L is half of LC, then what do we get? So let me just go ahead and graph this out. As a function of the, well, let me go from 0 to 1, and I will plot the output power at P2 let's go ahead and sketch this out as follows. And we'll do the other one. This is the sine squared curve. Okay, so this is, let's see, the sine squared is the red one, P3 over P1, and then the black one is P2 over P1. I can label this horizontal axis either with the phase angle phi, and we know that the sine squared and the cosine squared have a period of pi, right? And so half the period is pi over 2, full period is pi, 3 pi over 2, and 2 pi. Or I can label them in terms of L over LC, and what we want is we want complete switch over. Let's see, we want we want the output power to be completely over in waveguide number 3 at L over LC is 1/2. Okay, so when the length is half the coupling length, the input power is now completely sent to waveguide number 3. Let's see, Pn is up here, and if we have a coupling length of half, if we have a coupling region which is the length of the coupling length, then the power will completely transfer over to P3. I think I said it wrong here. This has to be a 1 and a 2 and a 3 and a 4. So when L is equal to LC, L divided by LC is 1, and we have complete power transfer over to the other side. And that makes sense because when phi is pi over 2, L is equal to LC, basically. You can see it just by looking at the argument, where phi is equal to pi L over 2LC. So when phi is equal to pi over 2, that happens only when L over LC is equal to 1. Okay? So this is the mathematical behavior of this. And I think there's a problem of yours that asks you to deal with this and ask the question, you know, how about if we have 1/3 of the power coming out on one output and 2/3 of the power coming out on another output. Notice that this all ignores excess loss. Okay. The final point to make about these directional couplers is that they're not always made with integrated optical devices. They're sometimes made with fibers. And in order to get the cores of two fibers together, what we have to do, okay, so additional points. The first one is that we can make fibered directional couplers by melting two pieces of fiber together. In a very controlled way. The second additional point is that we can notice that the coupling length depends on lambda, depends on the wavelength. And it depends on the wavelength because the shape of the mode depends on the wavelength. And the shape of the mode determines how quickly the energy goes back and forth here. And this implies that we can make what's called a wave division multiplexer. Out of these devices, such that on the input, let me go ahead and draw the device again here quickly. On the input we have lambda 1 and lambda 2, two different wavelengths, and if you set this up just right, you can get wavelength 1 coming out one and wavelength 2 coming out the other. And these are very commonly used application for directional couplers, both in the integrated optics case, but especially in the fiber directional couplers. So they make a lot of these things which are used in distribution networks, passive fiber optic networks. Okay, so that's directional couplers. Thanks.